friends, let us begin with the second module. In the first module, we have looked at what AI is and what are the problems which AI is trying to address, and so on and so forth. In this module, we are going to talk about a typical method which is used to handle most of the AI problems. That is called state space. What is it? We will talk about that. The problem is, most of the AI problem is that they are very hard to characterize. For example, take a case of finding out who the person is. Now, how will you write that problem? I am not asking for a solution. How will you characterize the problem? It is not that easy. Think of it, you will find hundreds of schemes and none of them will be most satisfactory. You can say this, you can't pinpoint on a typical thing which says this is going to be the thing. Okay, why? Because it is very hard to characterize. Let us take a simpler example. It is not all that simple, but comparatively simpler example of playing chess. How will you characterize a chess board? You can say, yes, great, I'll have an 8 into 8 matrix and provide positions of the pieces on the board, which in turn is the representation of a chess board. Great, but then I would say, give me all positions of that. How many such matrices you will provide? Think of it. Second thing, if I say, show me a move, how will I represent a move? Okay, one very simple way of doing it, you can see on the slide that you have one typical position on the left hand side, one typical position on the right hand side, and just show that the move is characterized by having the position of the pieces here, which is shown on the left hand side, and the result of the move is something that you have it on the right hand side. So, that is one way of showing, but then how many such moves can you write for chess? And believe me, if you start writing such rules, you will not be able to complete that thing in your lifetime. That many rules are possible. So, then that is not the right way, you will have to find some other way. So, the next slide actually talks about how you can write the rule in a little more flexible, little more general way. Okay. So, just see if pawn at this place and the next block is empty, then you just move that pawn there. The rule is written in a very simple programming like way, so you can easily understand. But even in this case, how many moves that we can write is going to be substantial. Not impossible to write, people have done it, but it is not going to be easy. Okay. So, this kind of representation is called state space representation. State space is basically an enumeration of all possible states that a problem can be in. And a move is something which allows you to move from one state to the other. In short, you can use moves to move around in state space and reach to the solution. That is what we are going to study in this particular module. So, let us first of all begin with the state space definition that we already have on the slide. Okay. Look at that. It says if at pawn black I j, that means is a black pawn at position I and j equal to 7. Now, if you look at that figure, it is the initial position. When j is 7 indicates that it is the initial position of that black piece. And empty I j minus 1, in fact, that is the next block. It says that the next block is empty. Not only that, next to next also is empty, you can move that piece forward, empty I j minus 2. Then you can say that at pawn black I j minus 2, you just move pawn 2 steps further, and where earlier the pawn was, that place is blank. This is a move. You may ask me, is it a good move? Let me tell you, no. Why? We are not looking at anything else. A good chess player would look at other things. We are not going to discuss that thing right now. We are only going to talk about legal moves right now and not complicate the matter for writing moves for winning. That is altogether a different thing. We are not going to address that right now. We are going to address a simpler problem of how one can represent using a state space. Okay. State space is about representing the problem in a computer understandable form. We have already seen the chess representation, the matrix representation and the move representation. We have already seen how specific and general move can be written. Let us take a very simple example. Chess is again a very hard problem because it contains so many moves. We are going to pick up a very simple problem called 3-4 Gandel water jug problem. Now this is also described in a book called A Line Reach. So we have two jugs. One is a 3-gallon water jug, the other one is 4-gallon water jug, and we have ample supply of water. What we want to have is 2 gallons of water in a 4-gallon water jug. We do not have any other measuring device and would like to have exactly 2 gallons of water in a 4-gallon water jug. How can I have it? Fine. One way to do it is this. We begin with 0 0 and you can see the sequence on the slide. Eventually what I get is 3 2. So a 4-gallon water jug will have 2 gallons of water at the end. That is great, I can solve it, but can a computer program do it? That is precisely what we are trying to do now. How can a computer program do it? So one way to do that is to use a state space representation, and that is exactly what we are going to do next. We skip that thing for a while. We will look at one more problem called 853 gallon milk jug problem. 853 gallon water jug, milk jug problem is little different. It is little more complicated because we have 3 jugs. Not only that, we begin with 8 gallon of milk completely filled. And now what we want to have is only 4 gallons of milk in that particular jug. We again do not have any measuring device with us. And exactly you can see on the slide one solution which begins from 800. Now that is the representation. 3 integers, simplest of representation of this particular problem. And you can see that at the end what we have is 440. That means 4 gallons of milk in the 8-gallon jug. Okay. In both cases, 3-4 gallon water jug and 853 milk jug problem, we have something called an initial state. In case number 1, we have 0 0, both jugs are empty. In case number 2, 800, the first milk jug is completely full. Okay. We also have a final state. For example, in the case number 1, we have 3 2, the case number 2, we have 440. Is a final state. So it is possible to have multiple initial and final states. For example, in case number 2, you might have 4 1 3 as the final state, and the earlier one also you can have 2 and 0 or 2 and 0 and 2, 3 and 2 is also possible. So there are multiple initial, multiple final states possible in other problems. When we see some other problems, we will see that there are many complexities are there. But anyway, we are not going to discuss that thing right now. What is the solution? Solution is about moving it across state space. Now we have that initial state and final state. So we said that we begin from an initial state, we move across in the state space using moves that we have. We will only be able to use legal moves. So we can't jump from one state to the other unless we have a legal move connecting them. So we start from the initial state, we move across the state space and will reach to the final state. And we have to use valid moves, as I said. Okay. For example, we can't move from 0 0 to 1 0 in case number 1, because how will you get 1 0? There is no measuring device available, you can't get that. Okay. So that is an example of an invalid move. And the other case, can you have a 4-gallon water jug with 3 in the beginning? You cannot. It is impossible because we do not have measuring device. So 0 0 to 3 0 is impossible. This is again an example of an invalid move. Not only that, for every problem which we take, there are some implicit assumptions. For example, when I am dealing with this most trivial of problems, we have some implicit assumptions. For example, when we are talking about water jug problem, we think that the water is available, we can pour the water out of the jug. In fact, our solution, you probably have seen, there are few places we are just pouring water out of the jug, because water is inexpensive, which is not there stated in the problem itself, but we assume that thing. Unlike that, we can't pour milk out of the jug. Why? Milk is expensive. You cannot pour it out. So these are assumptions, implicit assumptions there in the program itself. How to get them is a hard problem. Sometimes people say it is a question of common sense, but common sense, believe me my friend, is very uncommon. Okay. There is one example shown in the slide, you better see. 1 3 to 1 0 is possible. Why? You can just pour out 3 out of the jug. In case number 1, it is impossible to do something like that in the milk jug problem. How do you code them? It's not that easy. Not only that, there is one more thing. How its state is chosen. For example, there is something called 0 0. Let us begin. There are a lot of things possible. 4 3 is possible, 4 0 is possible, 0 3 is possible. How you decide a state? Not only that, once you have 0 3, again there are some other moves possible. Which move will you take and why? Okay, that's the next thing. Almost all, what my point is, almost all AI problems are harder than what you see, what you find them at the first glance. In our trivial cases, what we can do is just enumerate the states and pick up states, which is comparatively easy. Think of chess, you will not be able to do that, but for these trivial cases you can actually do it. You can also write a formula. Look at that, xy, where x belongs to 0 4 and y belongs to 0 3. So any value between 0 to 3, any value between 0 to 4 is something that you can write. It's that simple. And collection of all valid states is called a state space. What is solution? This is about beginning from an initial state, move around in state space and stop when any one of the goal states is reached. We have already seen examples of a general and specific rules. The PPT is talking about this. A 4 3 gallon jug problem, 2 rules, one is specific, the other one is general. The 853 gallon milk jug, again there is a specific and a general rule. And also a state space representation. Now look closely at this representation of 853 gallon water jug. It says, and we are only using a 3 integer vector value x, y and z. We say that the state space is represented by x, y, z, where x plus y plus z is 8. That means total amount of milk that we can have is 8. X, y, z greater than 0 or equal to 0, where we do not have negative values. X less than or equal to 8, the capacity of the x is 8. So you can have 8 or less. Y is less than or equal to 5, so capacity of y is 5, so you can have 5 or less. And z less than or equal to 3, that means x z value can be maximum 3. The initial state is 8 0 0. Okay. So this is how you represent the state space. Now let us see how we can define rules or moves. Sometimes the moves are known as or written as production rules. So we use that word here as well. Okay. The first rule says x, y, z. We have x, y, z in the jug. X is the amount of milk in jug, the 8 gallon jug. Y is the amount of milk in 5 gallon jug. Z is amount of milk in the 3 gallon jug. Where y plus z is less than 3. Total amount of milk in y and z is less than 3, then what you can do is you can pour everything in this, the 3 gallon jug. So that is what precisely it is doing. It just combines y plus z. Obviously the middle jug in that case will contain no milk, so that is 0. So x 0 y plus z. What if it is more? If it is more, then whatever you can fill the 3 gallon jug, and whatever is remaining is there in the 5 gallon jug. So that is what exactly next rule talks about. The third rule is talking about a case when y plus z is less than 5. So what you can do is, now earlier we are talking about pouring milk in 3 gallon water jug, now we are talking about pouring milk in 5 gallon jug. So you pour that thing inside and get it empty. So total amount of milk is less than 5 gallon, you can just pour it inside and get it empty. If it is not, you can pour everything that you can, and whatever is left is kept here. So that the next rule, it says x, y, z, y plus z greater than or equal to 5, you have x 5, though this is completely full, and whatever is remaining is here. Okay, now we are talking about the third case, the 8 gallon jug and 3 gallon jug. So if the x is greater than or equal to 3, so here we have more amount of milk, you can fill this thing, and whatever is remaining you can keep here. So that is the next one. But if the total is less than 3, So, you can pour everything here and this becomes completely empty. So, that is next rule. Okay. X, Y, Z. Now, x plus z is greater than 3, x plus z minus 3. What is that? If I completely filling this and rest is keeping here, and the 8, 9 and so on. You can read these remaining rules yourself, and you can see that they are completely self-explanatory. Okay. So, we are not discussing the rest of them. Now, how you solve this problem? Now, carefully look at how the solution is achieved. We begin with state called 800, the initial state. We move on to the state called 350, where we are applying rule number 9, and so on. You can see rule number 9 is applied, then 4, then 11, then 1, then 9 again, and then 2 and 11. They are applied, and what you get is the answer. Okay. So, this is how you can define a state space, you can have initial and final state, you can define moves and how you apply moves to solve a problem. Have we solved everything? No. There are few things which are worth pointing out. So, let us talk about. Okay. First, not all rules are used. We have not used all those rules which we have defined. So, the question is, should we define rules which are not used for solving a problem? How do we know that these rules are going to be useful for solving a problem? Big problem. It is quite possible that we may not write one rule without which we cannot solve the problem. So, that is first problem that we have not actually addressed. How have you come to know that this move, the set of moves is complete, which is going to, every move that we need is possible to be fetched from this thing? How do we know? That is the important problem. Anyway, so that is one thing which we will have to work on. Second, a clear indication of what start and end states and what are the valid states. For example, what in our case we can do, but think of a case of chess. How do you know that this is a valid state? In fact, there are more complex problems than chess. Okay, we will talk about some of them in due course. And set of rules. Okay, set of rules, again in this case we could write, but then in many other cases we will be talking about them. Okay, now let us summarize what we need as components. Okay, what are the components for solving this problem? First thing, we need a data structure for storing the state. In these trivial cases, we only need a 2 value vector and a 3 value vector, 3 integers only. That is all, pretty simple. But that is not going to be the case in most complicated problems. For example, think of a robot domain. Robot is a very important applications of AI. Assume that robot is moving around in a room. Now, think of the state that he has to look at. Ceiling above the floor, there is a floor beneath, there are objects around in the room, chair, sofa, lights, so on. So many things to store. Okay. So, state space in that case is pretty complex. Think of a moving car, an automated car, which is actually taking a lot of inputs from lot of sensors across, lot of cameras and all that. The data structure that you are going to use is pretty complex. So, it is not always be that simple. Anyway, so let us, okay, that is the second thing. When a rule is applied, there is something which should change the state. The current state is x. Now, for example, 800, that is converted to 5053. Now, how that is changed? There is something which stores the current state. There has to be something which stores the current state. So, that is something that mechanisms to store current state is very important. And logic also is required. Who changes that? In our case, it is pretty simple. We just do addition or subtraction. We have seen the rules are pretty simple, addition and subtraction. Not in all cases those simple addition and subtractions are possible. There are a lot of other complexities. How converting one state into another requires complex processing. And the most complex thing is that when there are multiple rules possible, there are not 1, 2, 3, 4 rules are possible. Which one should I choose? Now, that is a pretty complex problem, and that is where this power of computation, power of the technique resides. If you know how to do that, I have already discussed that in the previous module, that there is something called heuristic which can help us. but that is a pretty hard part of the state space representation and solving problems using state space. Okay, last 3 requirements, okay, quite exaggerating. For this simple problem, nothing. I only have 2-3 moves, and I can always test all those moves to see which one is better, but not in all cases. I have already talked about 2 cases, chess and robot domain, and even automated car domain, where this is just impossible. This is an example shown in the on the slide, the auto navigator problem, the moving car, an automated car. You probably have heard about Google car, that is self-driving car. It's possible for somebody to write rules for it. You can, but then when you write rules, how you define a state space is pretty dynamic. For example, how the navigator represents the problem itself moving across. You know how in Google Maps it's using the Google Maps Google car uses Google Maps, but how do you represent that? The problem itself, moving from one state, for example, moving from Ahmedabad to the Vadodara, how you do that? So that data structure, it's pretty complex. Consider the input coming from a lot of frames, sensors and all that, pretty complex. The speed, and again the decision is to be taken, the processing has to be pretty fast. When you are deliberating over where to move and there is a sudden obstacle, you will have to take an immediate left movement or something. How do you do that? So if it is not working that fast, it's not going to be that useful, that powerful. Okay. Number 6, which move to choose, as I said, is daunting for most of the cases. Even our trivial case, it's not easy. The 7-step solution, the solution could have gone in different direction. Pick up the 4th step. We could have applied rule number 9, 8, 6, etc., but we choose rule number 1. Why? In fact, we have already solved the problem. We have cheated actually and just instructed the program to choose rule number 1. We have not provided any logic for it. Well, okay, suppose we have a choice. How can we provide that? We don't really know. Right now, we don't really know. Okay, if we'll let us study about heuristic, we'll have some idea how we can choose one move out of most. Right now, we have no clue. Okay, problem in our case, the problem is pretty trivial, so we can solve it manually and can instruct the program to do it. As I said, it is cheating and it's not desirable. So why it is not desirable? For 2 reasons. When the program acts like this, it's basically working on the instruction of the designer, which is impossible for complex cases like chess. And second, what we want is to make the program more intelligent, to solve the problem itself, not the designer solving it and hard coding it in the program. We don't want that. So our goal is not achieved if you do it this way. Okay. Okay, now you might be getting the feel for the problems AI researchers are facing over the years. These simple programs are pretty hard on the face of it. Okay. You probably have heard about professional chess playing programs and something. If you read computer related information, probably you have heard about Garry Kasparov being beaten by a computer built by IBM engineers. You probably think that it is possible. There is a problem which is possible to be solved, but then we don't have programs which can play table tennis. We don't have programs which can play many other games. But still we have programs which can play chess. Why? Because chess is much more structured than many other cases, many other games. Even table tennis is comparatively much simpler to represent. Not only that, we have many heuristics possible. We have already talked about heuristics. For example, in chess there are many heuristics possible. One is if you have a move which controls the center, it is better than other moves. If we have a move which can check the opponent's king, it is better. If we have a move which can provide something called threat of fork, if you play chess, you know what I am talking about, otherwise you can just forget. It is better. So there are some ways of telling which moves are better compared to others, and that's why it is possible to build programs which can play chess. Not only that, it is also possible to mimic how the opponent plays. And the machine which has played Garry Kasparov was specifically designed to play with him. Okay, so it has all data about Garry Kasparov, how with the amount of moves and all that and so on and so forth. So it could do it, but otherwise it was, believe me, it's going to be hard. But anyway, chess is better program to be managed compared to many other programs. Why chess is solved? Because it's comparatively easy. But then, as I said, comparatively easy to represent. Remember, we are talking about represent things in state space. I give you a simpler problem to solve, rating an essay or rating a post. Can you do that by computer? Can you write a program to do it? No, it is not that structured, it is very hard. Okay, and it is also subjective. So that's not easy. You can't write algorithm, you can't represent that in a state space. Think of representing a problem of rating an essay or rating a post using a state space, and you learn that it is not that easy. Okay, if you can represent something using a state space, it is possible, because we have a structured mechanism of moving around in state space, starting from the initial state, use legal moves to reach to that final state. It is possible, but it is not possible in this case. Okay, or the other example which is shown on the slide, how to build a robot which can do all household chores. How you do that? It is not easy. Not, in fact, you probably have heard about a robot which makes pizza, but that's the only thing that robot can do, and only if everything is stacked exactly for its requirement. If it is not, it cannot do it. Okay, so that's the problem. Chess is quite structured, the other problems are not. Okay, and here are some heuristics that most chess programs use. Number of pieces, the respective rating. For example, queen is rated much higher than others, and king is rated much higher than everybody else, so on and so forth. Okay, let us recap what we have looked at in this particular module. We have seen that the AI programs, one of the major obstacles in solving problems, the AI problems, is to characterize them precisely. We have looked at one very simple method of characterizing AI problems called state space representation. A state space representation is about storing information in a form that there is something called an initial state, the problem's state in the beginning. When the problem commences, the problem is in the initial state. We have one more state which is called a final state. What we want is to have the problem in the final state once we completely solve that problem. We also have a lot of other states where the problem can be in. Okay, we call them valid states. We also have rules or moves which can move the problem state from one valid state to another valid state. Okay, and the solution basically is a method of starting from initial state, move around in state space using legal moves, and reach to a final state. As long as it is possible for somebody to represent anything in state space and write valid moves, it is possible to get answer to it. It is possible to encode it actually. Chess is very structured compared to others and seemingly complicated problem, but comparatively more structured, so people have solved that problem. And there are many other problems which are not possible to be solved, for example, rating an essay. Okay. We have already seen in this particular model, we have seen two problems, trivial problems. One is 3-4 gallon water jug problem, and the other one is 853 gallon milk jug problem. And we have seen how one can write the state space. It's pretty trivial using a vector. How can one write the moves, the 11-12 moves? How can you start from the initial state, apply moves, and reach to a solution? We have also seen what are the problems, what are the challenges in this. One major challenge that we have stressed is to choose a move. Now, which move to choose given some alternatives is pretty hard problem. And we have seen, in fact, we have hinted that one can use heuristics to determine which move is better than the other, which we are going to address in the next module.